Hello. Uh, Welcome to our applied statistics class. Okay, let's just begin. Well, let me introduce myself first. I am Chi Hong Wong. Okay, from the School of Pharmaceutical Science and Technology. Okay, but if you want to contact me, of course, I've got my email um, given here. But of course, if you want to find me at all, it will be easiest with WeChat. Okay, just send me the WeChat message privately or in our WeChat group, which you most of you are already in anyway. Okay, just give me a shout. Then yeah, that would be the quickest. If you prefer to send me emails, and of course, that will be my email. And of course, if you for those of you who might be uh, in the campus in Tianjin University in the campus, I'm actually in the old campus, building 24209. Okay, if you happen to be, I don't know how many of you are actually in Tianjin in China. Okay, for most of our students are actually abroad doing this, taking this course online. And sadly, I'm not sure. We can't do this course online live with you because, well, as you are probably aware that many of us are in different time zones and around the world, so it might be difficult for us to do these things. But having said that, I really need to think of a way. I really need to think of a way that you can do our exams at the same time. Okay, yeah, it'll be a bit tricky for us to do the exam together at the same time. If yeah, but well, we'll try to work out some way for that. But it'll be many weeks later. Okay, this course. Okay, applied statistics is 2 credits starting from this week 11. Week 11. We're here in week 11 now. We're here in week 11 all the way to week 18. Sorry. Okay. This is what we will be having here. Meeting, well, every Monday. But of course, since we're not since we're not doing this live or together or actually offline together in the campus, so there's no point in doing this. Well, like strictly like Monday 1:30 to 3:05, something like that. Yeah, that's what would happen if you guys were sorry, not 3:05. Sorry, to 5. That's what would be the case if you were in the campus, but of course, these don't happen to us. So I'll tell you what I'll do. I'll just record our classes here, like yeah, on my own. I'm doing this right now with myself here. I'll record these classes and I'll send you guys a video. Sometime once every week or sometime around Monday. Well, if we're keeping this Monday thing here, okay, and then we're going to do this from week 11 all the way to week 18, and then we'll have our exam afterwards. Okay, we'll have our exam afterwards. So sometimes about week 19 or week 20. Okay, see what you like. Okay, and see if we can figure out some ways to our exams. Okay, with some of those online platforms, or I simply or I one option might be I simply send out the questions as a whatever PDF file, and then to you guys, and then you just answer them, and then just return your answers to me like in 2 hours time, and that's all. Yeah, your final exam, it's about 2 hours. Okay, it'll be 2 hours for your final exam, and that's all you will have. Okay, since we're doing this online, and then even well, I'm just sending you guys a video, so there's no way we are taking attendance, and of course where as research students graduate courses were not that keen on giving homeworks, etc. So yeah, so at the end of the course there will be one single exam, and that will be all really. But don't worry about that. Hopefully it should be fairly easy. Okay. So here's me again. Okay. If you want me, okay, just, if you have any questions at all, just give me a shout in the WeChat, and that I'll try to answer sooner. Okay, and of course, if you have any problems downloading these videos, which I'm sure there might be problems with a few of you. Okay, so again, do let me know. We'll figure out some way. I'll send you guys through email, or some people suggest me doing this with some of those cloud storage platforms, or even if you prefer to do it on Skype or QQ, if you even have an account on QQ, etc., then yeah, surely we will have a way to send these videos. Okay, so let's just begin then. I understand that this is for, well, all of our graduate students in the university, so I'm sure that you guys are from different subjects. Okay, some people doing engineering and some people doing other sorts. Okay, so but you guys are research graduate students or research students, so I suppose you will be able to find some readings for yourselves. Okay, that's what research students are here to learn. Okay, to look for things for yourselves. But of course, if you prefer some readings for this particular course, then of course I've here got two of them, which I must say they are rather they might be a bit mathematical. Okay, it is mathematical statistics. So yeah, I'm here. This course is to give some mathematical backgrounds to the statistics that you might have done before. Okay, I understand some of you, okay, might have used statistics in your undergraduate studies, and of course in your experiments, if you did any experiments at all. Okay, so you might have used some statistical methods before, but here we're going to give you some mathematical background with them to go with them, so that you at least next time you press your Excel function buttons, or your whatever program things here, you might have some understanding of what you are doing. Okay, uh, if you prefer to have some books or other readings about the practical usage of the statistics, then of course by all means these two books they are not I'm not asking you to just read these two books, but there are tons everywhere. You can look them up from the library, or on the internet these days. Okay, these two are just my suggestions for this particular one, which you might find helpful. Okay, but if you don't worry too much, if some of these maths, if you read this book, if you find some of these maths too complicated that you might have never, but you might not have done before. Okay, try read them slowly. Don't worry about them if things go too difficult. Okay, and of course, as I said here, because we're all from different backgrounds, but we're all doing different subjects, and I'm a mathematician, okay, but of course not. You guys might not be. Okay, so I might here talk to you about some backgrounds that you might be required for this particular course here. Okay, so I don't like green. I'll use black again. Okay, so we might need some of these mathematical paragraphs. Hopefully, uh, most of them, okay, are easy to use, or you should be familiar. Okay, of course, we begin with talking about some elementary mathematics. So of course, you need to be able to do arithmetics, of course. Okay, if not, you have calculators. Okay, you have your calculators. Yeah, you have to be able to understand functions and all that. Okay, given a mathematical function, so you put in a value for x, you get a value for y, etc., etc. So using how these things work, possibly with graphs and all that. So you also need a little calculus. You also might need a little calculus. You might need to be able to do a little differentiations. Okay, as calculus. So that is differentiations, and integration. Okay, but of course, differentiation involves something like, okay, this. Okay, of course, we're not doing this. We're not doing exactly a calculus course in mathematics, so we're not going to give you anything too complicated here. So you need to know something about like the derivative of a function, like what it means. Okay, like if I give you an x squared, if I give you a function y equals to x squared, or f of x equals to x squared, okay, what is the derivative of this function? 2x. Okay, I'm sure you have seen this before, but what is more important about this is, what does that mean? What does that even mean? I need you to recall these things. The derivative of a function tells you how the function changes, the rate of change of your function. Okay, it tells you whether your function is increasing or decreasing, the trend of your function. The trend of function. Okay, if you look at graphs and all that, then it will be the gradient or slope. So if I may call this function like y equals x squared. Okay, so you need to know something like this. And of course, we need some calculus, differentiations, and of course, we also will have to be able to do some integration. Integration, that is integrals of something like, I don't know, for instance, a cosine of x. Okay, remember, I'm not going to give you anything too complicated here. Okay, you wouldn't see something too complicated here. So if we have something like cosine of x going from 0 to pi over 2, okay, yeah, I understand that still many people are still using degrees for angles, but mathematically we should have moved on to radians. So you use pi over 2 for 90 degrees, pi for 180 degrees, etc. So that cosine of x integrates and becomes sine of x. And then when you put your 0 and your pi by 2 in there, and gives you your 1. Okay? Yeah. That sort of thing. Okay? You must have seen this before. You must have done a little calculus. Well, most of you here. Okay, if you haven't done anything like that, yeah, I'll remind you as we go on, of course. A little linear algebra as well. So we have a bit about vectors, matrices, and all that. So if you're familiar with them, vectors. So you've got arrows, or if you have two-dimensional space where you have your XY plane, so that you get your arrows going that way. So with notations, I don't know which you prefer to do, like 2i plus 3j, something like this, or 2, 3 if it's written vertically like this, or occasionally 2, 3 written horizontally, as some people occasionally do. Okay, so something like this. When you do your physics, in school or in university, so you might have come across with these guys, and of course they have you may some people prefer to do it with a 2i plus 3j, that sort of notations where it means you're moving along horizontally by 2. You move horizontally with 2, and then vertically by 3. Okay, and you need and simple understanding of these vectors. So if you can add vectors together, multiplying a vector by a number so that it gets stretched longer, and that's all. Finally, okay, programming. Okay, I'm not the best person to instruct you about any programming skills. If you have done programmings before, if you have used statistical programs such as if you use like MATLAB before, or if you like do R or SPSS, that sort of programs, that's fine. Okay, if you know any of these things, good for you. Okay, I don't. Okay, most of our calculations can be done with Excel only. Okay, that's all I know. Okay, so we'll be doing if we need any calculations, it's programming. That's all. It'll be Excel. That's okay. So if I go into a bit more detail of these things, of course, so we'll need to we're using some of these. I'm introducing some of these notations that we often use. Okay, we'll keep writing these things, so we may as well understand what these mean. So for instance, the summation notations, if we have a lot of things adding together, okay, I've got 1 plus 4 plus 8, 1 plus 4 plus 9 plus 16 plus 25, etc. I've got a lot of numbers added together. I'm being too lazy to keep to writing the whole lot, or especially if I have to add all the way to some particular some specific numbers n. Okay, then I may consider using this summation notation, having this is the capital Greek letter S. This is capital Greek letter S. S for what? S for sum. That means adding a lot of things together. I'm adding what together? I'm adding k square here, for instance. I'm adding all the k squares here from k equals to 1 to k equals to n. So I'm starting with 1 square, 2 square, 3 square, 4 square, all the way to n square. I'm adding the whole lot together. Okay. Well, there's a formula for this sum, but I just don't remember. You can look them up from the internet for a formula book. Okay, but I'm using this notation here, the summation notation, if necessary. And of course, I can also add a lot of things together. Well, I mean, adding a lot of things together. I can have this n going off to infinity if I have to keep adding these terms together all the way to the end. Okay, forever, having k going to 1 towards infinity, like 1 over k squared in this case. Of course, it'll be silly if I just add k squared from 1 to infinity. Okay, it'll just be large. But if you add 1 over k squared, okay, just do 1 plus 1 over 4 plus 1 over 9 plus 1 over 16, etc. Keep adding this forever. I mean forever. As it turns out, this has a sum, has a finite sum. It equals to a certain number. Okay, which if you did your calculus or whatever math class before, then you might be familiar with this. And of course, sometimes I'm just being too lazy to keep writing k equals to 1 to k equals to n or whatever. I'll just put a k underneath there. sum with a k there. If you know what exactly to add together. You see, when we do statistics, we often end up with like a sample, a random sample of size n. So we have got n of our experiment results, the first one to the nth one. So we just like adding them all together. So we'll just, no one will get confused or with this notation here. Even if I don't put the limits in the summation sign, okay. If we can do sums, we can also do products. We can do a lot of things multiply together. Well, with this pi notation, with this product notation, this is actually the capital letter of the letter pi. Okay, the Greek letter pi. Okay, P for what? P for products, multiplying all the things together. That is, if you have the product of k, for instance, I'm multiplying k from k equals to 1 to k equals to n in a similar way, so that we have 1 times 2 times 3 times 4, etc., all the way to n. But of course, you must have you might be more familiar with the other notation, what we call the factorial notation, with an exclamation mark next to your n there. Okay, n factorial, meaning I'm taking all the integer, all the positive integer less than or equal to n multiplied together. N times n minus 1, n times n minus 2. So for instance, if you have what? If you have 5 factorial, that is 5 times 4 times 3 times 2 times 1, which is 120. Okay, and if you get something like 69 or 70 factorial, 69 or 70 factorial, these numbers these numbers goes up very quickly. If you if you have 69 or 70 factorial, it would blow up your any typical scientific calculator. It goes larger than a 10 to the power of 100. So so your pocket calculator will show error there if you go anything up to 69 or 70 factorial. I can't exactly remember, but 70 factorial is certainly going to be larger than 10 to the power 100. And more about this is by definition, okay, 0 factorial equal to 1. This is something people often forget of. Okay, 0 factorial is defined to be 1, not 0 times what? 0 times what is 0. So 0 factorial is exactly 1. Okay, just the same as 1 factorial. Okay, but this is our notation here. If you have to multiply a lot of consecutive integers together. Okay, so that where do you see these things? When you see these factorial things, for some of you here, okay, again, you might have seen these things before. What is this? This is NCR, or some people prefer to write it. Some textbooks write it this way, NR, like this. Okay, and your pocket calculator have this button here. Has this button NCR like this in your calculator. Okay, it says. But what is this then? This is the number of ways, the number of ways to choose or to pick out all things from n. Okay, so if you have n objects, okay, like you've got a bag, you've got 10 balls or etc. Okay, and you're picking out 3 of them. Okay, picking out 3 of them. Okay, 10 balls, all with different colors, etc. So you're picking out 3 of them. How many ways can you do it? Okay, so this what's called the C for combination here. The NCR thing here, the C here is for combination, the number of ways you can do these things, and it's defined as follows. Okay, for those of you who have seen the factorial notation, these things should come in the same chapter. Okay, so it's defined as n factorial divided by r factorial multiplied to n minus r factorial. Okay. Okay, if you've done anything like permutations and combinations in school, before in school or in university, you should be familiar with these notations, NCR, and then these factorial things. If you haven't done on the other hand, if you haven't done this permutation and combination things, yes. Speaking of permutation, there's also another one that's NPR, okay, or again some textbook will have this given as A. I don't know why it's called A, but ANR looking like this. But again, in your pocket calculator, it is given, well, actually, right next to your NCR button. It's right next to your NCR button, NPR button. Or sometimes you just press a shift and then you press your NCR button. That will be your NPR. This is your permutation. The number of ways to choose these objects. Well, where order matters. Okay. How exactly you're going to choose this? Well, the first one is the first ball coming from. Remember, I'm picking out 3 balls from 10. Okay. So if I pick the first one is red, the second one is blue, the third one is green, etc. It will be different. It will be different from if you pick out the first one is the blue one and the second one is the red one. Okay. So this is going to be a number slightly larger than your NCR. Okay. It's going to be a number slightly bigger than your NCR. You're not dividing by r factorial anymore, so it's going to be considerably larger. Okay, but that's not. This doesn't appear in our statistics calculations. Well, not usually. Okay, not usually. But NCR might be. And where do you see these things? After all, the number of ways to choose these things. Of course, if you did permutation and combination in school, then that's where you would meet them. But for those who didn't do this, you might have come across with this thing here. Okay, you might have come across with this object here before, what we call the binomial theorem. If you remember, if you have seen this before, okay, how do you expand the bracket 1 plus x all to the power n? How to expand the bracket 1 plus x all to the power n? Of course, if you want something simple, 1 plus x squared, you know that it's 1 plus 2x plus x squared. If you do 1 plus x cubed, you will do 1 plus 3x plus 3x squared plus x cubed, etc. Okay, but if you have 1 plus x all to the power n, I don't know what n is, like 50 or something, what would you do? What exactly do you do? Okay, there's a formula for this, and or you may have seen this picture before. Okay, the problem with recorded videos is that I can't actually ask questions and receive immediate response from you. Okay, so you might but has anyone seen this picture before? This has a name. Okay, it's called a Pascal's triangle. Pascal's triangle. Okay, but it's called different in China. But for us, it's called Pascal's triangle. It tells you how exactly to obtain these coefficients in our expansion 1 plus x all to the power whatever. Okay, it tells you if you do 1 plus x, it'll be just 1 and 1. If you do 1 plus x squared, you do 1, 2, and 1. You've got the coefficients like 1, 2, and 1. And the powers of x goes from 0, so that you have 1 there. X x squared, x cubed, etc. So that if you continue with this triangle, you have your 1 plus 5x plus 10x squared plus 10x cubed plus 5x to the power 4 plus x to the power 5 if you go to 1 plus x to the power 5. But you can continue with this triangle and then to as large the power as you like. But of course, if you want something like 50, you don't want to. Okay, the formula is given as follows. This is I'm running out of space here. Sorry, I'll have to. I tell you what, I'll move that underneath. Okay, so if you actually happens to have 1 plus x all to the power of n, 1 plus nc1 times x plus nc2 times x squared plus dot 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 plus nc n minus 1 to the x to the power n minus 1 plus finally x to the power of n. Okay, these numbers, the numbers on our Pascal's triangle, or these coefficients, if you have to expand a bracket like this, 1 plus x to the power of n, they are from your combinations, these coefficients here. Okay, the NCR thing. Sometimes it's written as NCR, and occasionally, okay, in some textbooks, and certainly that's what I'm going to use in this course, I'll just write it as NCR. Vertically with a bracket like this, it looks like a vector. Yes, it looks like a vector, but I'm sure when I actually use this notation in our probability distribution, I'm sure you wouldn't be confused with vectors. Okay, and CR, I'm just doing this with a looking as if it's a vector, but it's not. Okay, yeah. Either case, if you have done your binomial theorem, if you've done your binomial theorem or your permutation combinations, that's where you would have met this factorial notations or combination permutations notations. Okay, calculus, as I said earlier. Okay, if I have a function like y equals f of x, you need to you might need to be able to do a little differentiation. Okay, I'm not giving you, remember, I'm not going to give you something too complicated. This is not a calculus class. Only the basic ones will do. So if you have x squared, it becomes 2x. If you have x cubed, it becomes 3x squared. Okay, remember, if you have powers of x, you multiply by the power and then you lower the power by 1. Yeah. If you have sine function, it becomes cosine. Cosine of x becomes minus sine of x. These standard results, standard results for basic elementary functions can be found everywhere. So you can look them up from any formula book or internet or textbooks, really. Okay, but the thing is, when you have our derivative of a function, what does that even mean? Okay, the rate of change of the function tells you how it changes. That is when we can look for the maximum or minimum of a function, which we can check out the maximum or sometimes local maximum or minimum of our function. This is where the gradient of the function equals to 0. Okay, and most of the functions that we'll be doing will be differentiable. Okay, if you're familiar with these terms, most of these functions will be differentiable, smooth, nice smooth curve when you draw them out. Okay, so the local maximum or minimum of the function will occur when the derivative is 0. You see, we often interested to find the maximum or the minimum of a function. Like what? When do we care about maximum or minimum of a function? Well, of course, I can give you some examples in calculus. If you, but of course, we're doing statistics. So let me give you one. If you do if you do experiments, we often end up with graphs like this. Okay, I have to say I'm only a mathematician. I haven't done any experiments for a long time, but very often we end up with a lot of experiment data trying to establish or to prove if there's any relation between a variable x and y, so that we have a lot of these plotted on our xy plane. And I've got a lot of points. What you used to do is, what you would do here is you would draw a little straight line going through these guys. Well, there's no, well, because we're doing experiments, there are all sorts of errors. Says your straight line is unlikely to go through all the points, but we are going to draw a line of best fit. Sorry, can't spell. We have what's called a line of best fit. You have done this before, I'm sure, for your experiments, even for your experiments when you were in school. Okay, but how do we determine such a line? How do we determine such a line? Where should that be? Okay, in the old days when we were in school, I remember taking a little ruler, just place it on the graph and look for one that's kind of alright, where there will be as many points above the lines as the points below the line. Okay, roughly the same. So that's the way we used to do in school. But of course, mathematically, we can do better than that. Okay, statistically, when I'm sure if you have done this, if you with Excel, okay, there's a little. If you have done this with Excel, then you plot these things on the graph, you can ask Excel to actually give you the line of best fits for you, and it'll give you the equation as well. Okay, we'll eventually talk about how we obtain these. We'll eventually talk about how to obtain these equations. Okay, the equation for the line of best fit. But the idea about the line of best fit is to make sure that to have a line so that the error, okay, your experiment data, these little points on or away from your line, okay, the difference of these things, the total of these errors, if you like, okay, the difference of each of these from each of these points, your experiment data to your line, the total of them to be minimum. Okay, want to make sure that if I add all the errors together, if I just draw my silly straight line anywhere else, okay, I might get a lot of errors. Okay, but the line of best fit, as we call best fit, is so that the total error, if you like, okay, or in fact square of the errors, okay, to be minimum. That's where our calculus applied, where we have to look for the minimum of a function. Okay, in that case, not only that we may have a function with one variable like f of x becoming f prime of x, we might also need to talk about functions with more than one variable, so that we end up with partial derivatives. In the case where your function depends on more than one variable, okay, in the old days when your function has one variable only, like x squared, then you differentiate it, x squared becomes 2x, etc. But when your function has two variables, like x squared plus 3xy, okay, it has x, it has y. When you talked about the derivative, you have to be very careful specifying which variable you're differentiating with respect to. So we will talk about dz over dx and dz over dy separately. The rate of change of the function with respect to x, when you change x only, that means you're keeping y constant. Dz over dy, you're changing y only, so that means you're keeping x as constant. Okay, so that these again, we are only going to look at basic. We're going to look at basic functions. So if you have something like x squared plus 3xy, for instance, when you differentiate with respect to x, yes, x squared becomes your 2x, just as usual. And then 3xy, on the other hand, you have to think of y as a constant. We're changing x only. So y would be like a constant, 3y times x, so that derivative is simply 3y. Similarly, if you take this silly function to differentiate with respect to y, x squared, because we're looking at our x as a constant, x squared would be just like a constant differentiating with respect to y, it will be 0 and giving you 3x only. Yeah. Of course, we'll get to these. We'll remind you as we go on if we come back to these things again. Okay, if you have done this before, good for you. If you still remember any of these things from before, good for you. If you don't remember any of these things, or if you haven't done anything like this before, don't worry. Okay, we'll keep reminding you as we go on, and then you can keep pick them up sooner or later. Okay. Integration, of course, our integration is a fundamental theorem of calculus. The integration is really, in a way, the opposite of your differentiations. Okay, taking your 2x back to x squared, something like this. Okay, if I have a function f that I need to integrate, we need to think of a function, big F, think of a function whatever that gives you the derivative exactly little f. And then we just pop our limits in there, b and a, and then we do a little subtraction. That will be the integration. Done. The definite integral. And again, what does that mean? It means this integration tells you the area under the curve. If you have a function, the f of x here, okay, if you have a function f of x here, well, provided your function is bigger than or equal to 0 at all times, which again, for probabilities, it is definitely the case. Okay, the area under the curve, is given by this integration. Okay, that's why we might consider doing some of these things at all. And of course, if you are familiar with some of these probability distributions, such as the normal distribution, remember the bell-shaped curve, etc. Yeah, the probabilities is given by the area under the curve, which, as we shall see, how to do these integrations. Vectors, matrices, again, our notations will be, well, usually in column vectors. If you have a vector with, if we ever get, by the way, if we might or we might not get to topics where we need to apply matrices. Okay, but just in case, okay, our vectors it's given in column vectors mostly, but it can be written in rows. Okay, so that if you have our xy plane, or if we have our three-dimensional space, okay, if you have your x, y, z three-dimensional space, etc., or even if you have an n-dimensional vector space, then okay, I'm happy if you want to use your 2i plus 3j, that sort of notation, but writing it as a column vector 2, 3 will be just as good. Okay, especially when it comes to calculations with matrices. Okay, when it comes to calculations with matrices, where you have to multiply by a matrix. Okay, a matrix is really just a bigger vector, if you like. Okay, a rectangular arrangement of numbers where we can have m rows and n columns. Okay, m rows and n columns, having a matrix like A, I, J, or a like this, giving you each of these elements in the matrix. Each element, I've got lots of numbers here, m times n, that many of them. Each of them will be given an A11, A12, and A22, A35, etc. Okay. Just like vectors, because they are just bigger vectors. Okay, if you think of these matrices as bigger vectors, you can add them. You can add their vectors. You can subtract them just like normal. Okay, you can take your matrix, multiply to a constant number, no problem. Okay, but multiplications of matrices. Okay, multiplication of matrices might be a bit more complicated if you have never done this before. Okay, matrices. If you have 3, 2, 3, 4, 5 to multiply to something like 1, 0, minus 1, 2, and then I'll do one more. I'll do 4 minus 2 again. Something like this. Okay? How do you multiply two matrices together? Okay? Like the one where the thing is, if you have to multiply two matrices together, okay, you have to make sure that the one from the left, must have the same same number of columns. In this case, 2 columns. Okay, as the number of rows for the other one. Okay, the one on the right, you must have exactly the same number for the rows. So you have 2 columns to multiply to something with 2 rows. Because the way we multiply these matrices together is simply to take these guys, take these numbers, in this case 2 and then 3 there, to multiply to the corresponding numbers here. Okay, in this case I'll do 2 times 1, 2 times 1 plus 3 times 0. This would be my first entry. This would be my first number in the product of the two matrices. Okay, if I give them names like A and B. Okay, for the product here, the first entry will be this 2 times 1 plus 3 times 0. Okay, the row multiplied to the column in the sort of dot product kind of manner. Okay, and similarly, if you do the other one, the next one will be 2 times minus 1 plus 3 times 2. And similarly, 2 times 4 plus 3 times minus 2. Okay, people often mess up with the signs when they multiply matrices together. Okay, and similarly for the second row, we'll do 4 times 1 plus 5 times 0. Okay, just look at the rows and multiply to each corresponding columns. The second row to multiply the first column, second column, and the third column. 4 times minus 1 plus 5 times 2. And 4 times 4 plus 5 times minus 2. And then you will obtain your product like 2, 4, 4, 6, and then 2, and finally I will multiply 2 minus 2, so I've got a minus 10, 4, 4, 16, I've got another 6, like this. This will be A times B. Okay, simple as that. You just multiply the corresponding row to the columns for each of these entries. Don't worry too much about this notation here. I've got a Cij equals to the sum of whatever Aik times Bkj, that sort of thing. Yeah, is the way we write it if you prefer to do it with a summation notation, but it's kind of complicated to read if you are not familiar. But the thing is, you notice that the matrix A will have to be M times P, and your matrix B will have to be P times N. The same number of columns. The number of columns in A must be the same as the number of rows in B. That's the key to this multiplication to work. If they don't come in the right size, you can't multiply them together. Okay, if they don't come in the right size, I mean that is the number of rows the number of columns for the first one and the number of rows for the second one. If they don't match, you can't multiply the matrices together. But when they do, okay, you'll get an m by n matrix out of this. Given where each of the entries is given by this expression, okay, or simply with this calculation, taking the rows. Okay, if you want a 2, 3 entry, for instance, if you want a 2, 3 entry, that is this one here, second row, third column. If you want 2, 3 entry, then what you need to do is take your second row from A, and the third column from B. If you want a 2, 3 entry, row 2 to multiply to your column 3, and just multiply each of these corresponding numbers and add together. That's what it means. What this expression means, really. Okay, so nothing to worry about. Okay, it looks ugly. Yes, I know that. And similarly, if you are doing this with a matrix to a vector, okay, if you multiply matrix to a vector, which is really just a small matrix, a matrix with one single column, that is all. Okay, if you want to do it, then it can be done in a similar way. Okay, a matrix multiplying to a vector. Okay, so let's just stop here for a moment and take a little break, and then we can continue with a bit more with the statistics.